Picture this. A 200-package Monorepo. 50 engineers. Every push to main triggers a full TypeScript compilation. 4 minutes. Every single time. That is not a minor inconvenience. That is 200 engineer hours burned every single day on nothing but waiting for TSC to finish. At an average loaded cost of $50 per engineer hour, that is $100,000 per day. $1 million per year. Vanished. Not a bad architectural decision. To the compiler itself, and here is what makes this truly dangerous. Most engineering organizations never measure this cost. It hides inside CI dashboards as an accepted baseline. It gets labeled normal for a project this size. But normal does not mean acceptable. TypeScript's compiler was built in 2012 on a single-threaded JavaScript runtime. And for over a decade, that architectural ceiling has been quietly every team that scaled beyond a certain threshold. The question is not whether this is a problem. The question is how deep it goes. And that is exactly what this lecture will answer. In March 2025, the TypeScript team at Microsoft made an announcement that sent immediate shockwaves through the developer community. TypeScript 7 would ship with a native compiler, rewritten entirely in Go, delivering a 10x speedup over the current TSC. But here is where most engineers made a critical mistake. They heard text faster and stopped thinking. They treated it as a marketing headline, filed it under nice to have, and moved on. That is exactly the wrong response. Because this is not a performance optimization. This is a structural dismantling of an architectural constraint that has existed since TypeScript's inception. The decision to use Go, not Rust, not C++, not a JIT-optimized JavaScript runtime, is itself a profound technical statement. It reveals how Microsoft prioritized parallel compilation throughput, memory safety without GC pauses in critical paths, and portability of native binaries across platforms. Each of those decisions has a direct consequence on how you design your build pipeline, your Monorepo structure, and your CI strategy going forward. Understanding the architecture behind the number is what separates engineers who can act on this information from those who simply wait for the migration guide. In the sections ahead, we will dissect every layer of that decision, starting with what the original compiler could never escape. Before we go deeper into the architecture, let me be explicit about what you will walk away with. Lectures about new technology releases often leave you informed but not equipped. This one is designed differently. By the time we reach the final chapter, you will be able to do 4 specific things. First, you will be able to explain precisely why Microsoft chose Go over Rust. Not with buzzwords, but with a structured trade-off matrix grounded in compiler workload characteristics. Second, you will be able to identify which phase of the TypeScript compiler pipeline is responsible for majority of latency in any given project, because the bottleneck is not always where teams assume it is. Third, you will be able to evaluate the Go rewrite decision using the same framework a principal engineer or an engineering director would use, covering portability, ecosystem maturity, concurrency model fitness, and long-term maintenance cost. And fourth, you will be able to redesign a CI pipeline to extract maximum benefit from TypeScript 7's parallel execution model. These are not abstract learning goals. They are the 4 questions we'll face in the next 12 to 18 months as TypeScript 7 moves from beta to production. Now, let us begin by going back to where the original compiler started, because you cannot understand why it needed to be replaced and understand how it was built. The next chapter will show you the ceiling it was always going to hit. Before we tear anything down, we need to understand exactly what we are tearing down. The original TypeScript compiler, TSC, is a 4-stage pipeline, and every stage has a very specific job. Stage 1, this tokenizes raw source text into a flat stream of tokens. Stage 2, the parser consumes those tokens and builds an abstract syntax tree, the AST, which is a hierarchical representation of your code's structure. Think of it as a blueprint, not a building. Stage 3. The binder walks that AST and creates a symbol table, connecting every identifier, every variable, class, function to its declaration. And Stage 4. The checker performs type inference and type compatibility validation across the entire symbol graph. Now here is the critical insight most developers miss. These stages are not fully parallelized in the original compiler. They run sequentially in a single Node.js process on a single thread. That sequential dependency is the architectural constraint we are ultimately here to discuss. But before we get to the ceiling, let us look at the room itself, starting with the most notorious file in the entire TypeScript codebase. If you have ever cloned the TypeScript repository, you have seeker.ts. At over 100,000 lines of code, it is one of the largest single source files in any major open source project. This is not an accident. It is a deliberate architectural choice made for performance reasons within the JavaScript runtime model. The type checker is responsible for the most computationally expensive operation in the entire pipeline. Structural type compatibility. When you write a generic function that accepts a complex intersection type, the checker must recursively walk every member of every constituent type to verify compatibility. Single call site. The checker also maintains an enormous internal cache, type identity memos, relation caches, inference context stacks, all on the V8 heap. And here is the killer detail. This cache cannot be shared across files in a parallelized way, because type relationships are global. A type defined in file A can affect the validity of an expression in file Z. That global dependency graph is what makes checker both the heart of TypeScript's correctness guarantee and the single biggest bottleneck in your build. Now ask yourself, what happens to this bottleneck when you double your codebase size? The answer is not what you expect, and we will quantify it shortly. After the type checker clears every expression, the final stage is the emitter, and compared to what came before, it is almost relaxing. The emitter takes the fully type-checked AST and performs a relatively mechanical transformation. It strips type annotations, transforms TypeScript-specific syntax like enums and decorators, and writes out plain JavaScript. In parallel, it generates declaration files, the DDTS files, which encode the public type surface of your module for consumers. Source maps are generated here as well, mapping output positions back to original TypeScript locations for debuggers. Now here is an important architectural observation. The emitter is cheap because it is a pure tree transformation. It does not need to reason about global type relationships. It just walks the AST and outputs text. This is why transpile-only tools like sbuild and Babel can strip TypeScript types almost instantly. They only implement the emitter's job, skipping the checker entirely. But you lose type safety when you do that. The Go rewrite does not take that shortcut. It reimplements the full pipeline, checker included, and still achieves a 10x speedup. That tells you the problem was never the emitter. The problem was always the runtime executing the checker. And that runtime is what we examine next. Here is a question that should bother you. Why does a compiler, a program whose entire job is to process text and output text, need a garbage collector? It does not. And yet, because the original TypeScript compiler runs on Node.js over the V8 JavaScript engine, it inherits every runtime cost that V8 imposes. Let us enumerate them precisely. First, warm-up cost. V8 starts interpreting bytecode before it decides which functions are hot enough to JIT compile. For a long-running server, this amortizes away. For a compiler invocation that runs and exits, you pay warm-up cost every single build. Second, garbage collection pauses. The type checker's internal caches, relation maps, inference contexts, symbol links, generate enormous amounts of short-lived heap objects. V8's generational GC must periodically stop the world to collect them. In large TypeScript projects, GC pause time is measurable in hundreds of milliseconds per build. Third and most fundamentally, single-threaded execution. JavaScript has one event loop, one call stack. The entire checker TSCs, all 100,000 lines of type inference logic, runs on exactly one CPU core. On a machine with 32 cores, 31 of them sit idle while your TypeScript build runs. This is not a tuning problem. This is an architectural ceiling imposed by the runtime choice. The question Microsoft eventually asked was, what if we remove the runtime entirely? Microsoft did not simply accept these constraints. Between 2018 and 2023, the TypeScript team shipped a series of increasingly sophisticated workarounds. And it is worth tracing this evolution, because each workaround reveals exactly which wall they were trying to climb. In 2018, TypeScript 0.0 introduced project references, a way to slice a monorepo into independently compilable subprojects, allowing TSC to skip rechecking unchanged projects. In 2019, to speedup was added, a persistent cache file that records the results of the last incremental build, so the checker does not revalidate files that have not changed. Watch mode and the language server protocol enabled incremental rechecking on file save, amortizing checker across a development session. These are genuinely impressive engineering solutions, and they worked, up to a point. The problem is that every one of these optimizations is fundamentally additive. They reduce the number of times you run the expensive operation. They do not make the expensive operation cheaper. When your codebase crosses a threshold, typically 500,000 lines or more, even the incremental path through checkerpoint TSS becomes slow enough to break developer flow. Internal Microsoft teams were reporting that even incremental builds on their largest repos took over 30 seconds. That was the moment the team concluded, we have optimized the workarounds as far as they go. The ceiling is the runtime itself. And removing a ceiling requires a different building entirely. Now we arrive at the core architectural insight of this entire lecture, and once you see it, you cannot unsee it. TypeScript's type system is structural, not nominal. This means that when the checker evaluates whether type A is assignable to type B, it does not look up a registry entry and compare two identifiers. It recursively walks every property, every method signature, every generic parameter, every conditional branch of both types, and compares them structurally. For simple types, this is fine, but consider a large monorepo where you have complex generic utility types, deeply nested map types, conditional types with for clauses, recursive template literal types. The structural comparison between two instances of such a type is not on in the number of properties. It can be on or worse, because each level of nesting multiplies the comparison tree. Now combine that with cross-file dependencies. When file B imports a type from file A, and file C imports from B, and file D imports from C, the checker must propagate type compatibility decisions across that entire dependency chain. In a monorepo with 1,000 files, a single type change at the root can invalidate and re-trigger structural comparison across hundreds of downstream files. This is why your build time does not double when you double your codebase, quadruples. This superlinear scaling behavior is the fundamental mathematical reason why the Go rewrite targets 10x improvement, and why no amount of JavaScript optimization was ever going to close that gap. In the next chapter, we will examine exactly why Microsoft chose Go, and not Rust, to solve this problem. The answer reveals a decision matrix that has profound implications for how we think about compiler infrastructure in 2025. In the previous chapter, we hit the ceiling of the JavaScript-based TypeScript compiler, a single-threaded, GC-constrained, inherently sequential architecture that simply cannot scale to the demands of modern codebases. Now Microsoft faces a decision that will define the next decade of TypeScript tooling. Which systems language do you write a 300,000-line compiler in? This is not a religious debate about favorite languages. This is a structured engineering decision with 7 measurable dimensions. Performance ceiling: can the language actually deliver 10x throughput? Developer familiarity: can the TypeScript team port checker point ETSID without a 2-year learning cliff? GC behavior: does the runtime's memory model fit a batch compiler workload? Memory model: can shared mutable AST nodes be expressed safely and idiomatically? Cross-platform compilation: must the binary ship natively on Windows, macOS, and Linux without friction? Ecosystem maturity: toolchain, frameworks, and profilers production grade? And finally, porting fidelity: can the new compiler produce bit-for-bit identical type-checking results? Every language choice lives at the intersection of all 7 dimensions simultaneously. And here is what makes this decision fascinating. The answer that scores highest across all 7 dimensions is, in note, the one most developers would have predicted. Let's confront the elephant in the room immediately. The systems programming community in 2024 has a near consensus answer for what do you rewrite a large C or JavaScript codebase in for maximum performance. And that answer is Rust. Rust offers zero-cost abstractions, no garbage collector, deterministic memory deallocation, and a compiler that makes data races physically impossible. So why did Microsoft choose Go instead? The borrow checker. That single feature, which is simultaneously Rust's greatest strength and its most notorious barrier, became the decisive disqualifier for this specific project. Here is the core problem: the TypeScript compiler's checker TS. The 50,000-line heart of the type system is built around shared mutable AST nodes. Multiple checker functions read and write to the same symbol table entries, the same type inference caches, the same diagnostic lists, all at overlapping points in the execution flow. Expressing this pattern in Rust without unsafe blocks or pervasive arcmutex wrapping is not just difficult. It requires a fundamental architectural redesign. As Anders Hejlsberg's team publicly noted, the cognitive overhead of mapping JavaScript's implicit object reference model onto Rust's explicit ownership model would have made a faithful, incremental port essentially impossible. The goal was not to redesign the compiler. The goal was to rewrite it in a faster language while keeping every semantic guarantee intact. Rust demanded a redesign. That disqualified it. But wait, does Go's collector actually hold up under the load of compiling a 10,000 TypeScript monorepo? The numbers are about to surprise you. Now let's put the performance argument on the table with actual precision. Because the common assumption that Rust is all faster than Go is technically true in some workloads and completely irrelevant in others. The distinction that matters here is throughput versus latency. Latency-sensitive workloads, game engines, real-time audio processing, OS kernel modules, need deterministic, sub-millisecond response with 0G pauses. For these, Rust's zero-cost abstractions and manual memory control are genuinely irreplaceable. But a TypeScript compiler is not a latency-sensitive workload. When you run TSC on a large project, you are waiting for a batch job to complete. You care about total wall clock time, that is throughput. You do not care whether individual memory allocations take 50 nanoseconds or 200 nanoseconds, as long as the entire compilation pipeline completes 10 times faster than before. Go's runtime overhead, its GC, its goroutine scheduler, its slightly fatter pointers, cost somewhere between 5 and 15% compared to equivalent Rust code in throughput-bound tasks. But Go's native support for parallelism through goroutines can recover that 15% and then multiply the total throughput by a factor of 4 to 8 on an 8-core machine, something the original JavaScript compiler could never do at all. The performance gap between Rust and Go is measured in percentages. The performance gap between both of them and single-threaded JavaScript is measured in multiples. Microsoft was not choosing between good and great. They were choosing between two forms of great. And Go won on the axes that actually move the needle for a compiler. Let's spend a moment on Go's garbage collector specifically, because this is the argument Rust advocates most frequently deploy against Go in performance-critical contexts, and it deserves a precise rebuttal. Go's GC has undergone a remarkable evolution. Since Go 1.5, the runtime uses a trickler concurrent mark and sweep collector that runs almost entirely concurrently with user goroutines. By Go 1.4, the world, pauses were reduced to sub-millisecond territory, typically under 500 microseconds even for multi-gigabyte heaps. For a language runtime GC, that is extraordinary. Now contrast this with the TypeScript compiler's actual allocation pattern. The compiler allocates millions of small, short, last nodes per compilation run. These are created during parsing, used during type checking, and then become garbage simultaneously when the compilation unit completes. This is textbook generational garbage collection territory, a workload that Go's allocator and GC are specifically optimized for. Go uses a thread local bump allocator for small objects, which is among the fastest allocation strategies possible. The result, Go's GC is not a liability for a compiler workload. It is tuned for exactly this allocation pattern. Rust's RAE drop system is superior for long-running servers with unpredictable allocation lifetimes. But for a compiler that allocates in bulk and releases in bulk, Go's GC is genuinely the better engineering fit. The question now is, where does Go deliver its most decisive advantage? The answer is not in memory management at all. Here is where Go's architectural advantage becomes decisive. And this is the insight that explains the 10x performance number more than any other single factor. The original TypeScript compiler runs on Node.js. Node.js is single-threaded. The entire compilation pipeline, parsing, binding, type checking, emit, executes on one CPU core, one file at a time sequentially. On a 16-core developer machine, 15 cores sit idle while TSC runs. This is not a Node.js limitation that can be patched. It is a fundamental consequence of JavaScript's single-threaded execution model and the TypeScript compiler's shared state architecture. Go's concurrency model eliminates this constraint entirely. Goroutines are lightweight user space threads. Each costs approximately 2 kilobytes of initial stack versus megabytes for OS threads. The Go runtime scheduler multiplexes thousands of goroutines across available CPU cores, with work stealing for load balancing. For a TypeScript compiler, this means each source file can be parsed in its own goroutine. Type checking can be parallelized at the module boundary, and the diagnostic collector can aggregate results from concurrent workers safely using channels. The Go channel primitive, a typed, synchronized mesh pipe between goroutines, gives you safe concurrent communication without the low-level mutex complexity that plagues concurrent C or even concurrent Rust code. The result is that the Go TypeScript compiler can saturate all CPU cores during a compilation run. On an 8-core machine, this alone delivers roughly 5 to 7 times the throughput of the sequential JavaScript implementation, before any other optimization. Combined with Go's faster raw execution, the 10x claim becomes not just credible but conservative. And in the next chapter, we will go inside the Go compiler's architecture and measure exactly where each factor of improvement comes from. Every performance argument becomes irrelevant if the faster compiler produces different type checking results. This is the constraint that Microsoft treated as an absolute non-negotiable. The Go compiler must be a semantically equivalent implementation of the JavaScript compiler, not a spiritual successor, not a redesigned type system. A faithful port that passes the same test suite, produces the same diagnostics on the same inputs, and is safe to substitute in CI pipelines without triggering false positives or false negatives. This requirement, let's call it the semantic equivalence constraint, profoundly shaped the language selection. The TypeScript test suite contains tens of thousands of baselines, golden output files that record the exact diagnostic messages, type assignments, and declaration emit results for specific inputs. Every change to the compiler, in any language, must preserve these baselines. The process the Microsoft team followed was methodical. Port a subsystem, run the baselines, Compare output character by character, investigate any divergence, fix the port, repeat. Go's straightforward imperative programming model, its explicit loops, its simple structation, its pointer semantics, made this port verify fix cycle tractable. The TypeScript team could read JavaScript, checker logic on the left screen, and write equivalent Go on the right screen, with a direct structural correspondence. Rust would have required the team to simultaneously redesign data ownership and verify semantic correctness, two conflated concerns that make debugging divergence extraordinarily difficult. The separation of concerns that Go enabled was not a soft engineering preference. It was a practical requirement for maintaining a living compiler during a multi-year port. Let's make the porting fidelity argument concrete with the specific data structure that makes or breaks this entire decision: the AST node. The TypeScript compiler's AST is built from JavaScript objects, which are, under the hood, heap-allocated reference types. When the checker visits a call expression, it holds a reference to the same AST node that the binder annotated, that the emitter will later traverse, and that the language service will expose to VS Code's hover provider. Multiple components share the same physical object in memory. In Go, this maps directly and idiomatically onto pointer-based structs. A Go struct allocated on the heap, which Go's escape analysis handles automatically, is referenced by pointer, shared freely across Go routines when protected by appropriate synchronization, and has a familiar read-write access pattern. The mental model is identical to JavaScript's object references. In Rust, this pattern immediately collides with the ownership system. A single AST node cannot have multiple owners without arc, Rust's atomic reference counter. Every shared reference becomes arc clone at the point of sharing and arc drop at the point of release. Hot paths through the type checker, which traverse shared nodes millions of times per compilation, accumulate atomic increment and decrement operations. The resulting code is neither ergonomic, nor is it a faithful structural port of the original JavaScript logic. It is a Rust idiomatic reimplementation of the same semantics. For Microsoft's port strategy, the difference is critical. Go lets you port checker.ts. Rust makes you rewrite it. And that is ultimately why the TypeScript team made the choice they made, and why in the next chapter, we will see exactly how the Go architecture exploits these structural advantages to deliver consistent, measurable, tense performance in real-world compilation benchmarks. Let's start with a number that will reframe everything you think you know about TypeScript's performance ceiling. Every single time you run TSC today, Node.js must first JIT compile approximately 250,000 lines of TypeScripts, including the notorious checker.ts, which alone weighs in at over 45,000 lines. That cold start JIT cost on V8 consumes anywhere to 100 milliseconds before a single character of your source code is even read. This is not a TypeScript problem. This is a fundamental architectural constraint of hosting a compiler inside a runtime that was designed for long-lived server processes and browser tabs, not for millisecond-sensitive CLI invocations. The Go binary eliminates this entirely. It compiles to native machine code ahead of time, and when you invoke it, the OSLer maps the binary directly into memory, and execution begins in under 5 milliseconds. That delta, 200 milliseconds saved on every invocation, is just the startup tax. The actual type-checking speedup is layered on top of this. But here is the question you should be asking. If startup cost is only one piece, what are the other architectural levers that compound this into a 10x gain? The answer starts with what AOT compilation does to your hot paths. Now let's go deeper than startup time, because this is where most analyses stop, and where the real architectural story begins. When Go compiles the TypeScript compiler source to a native binary, it applies a set of static optimizations that V8's JIT can only approximate, and only after collecting runtime profiling data across multiple invocations. Consider function inlining. The Go AOT compiler can inline small, frequently called functions, like the dozens of typeguard predicates in the type checker, at compile time, with zero runtime overhead. V8's JIT must first observe these call sites across thousands of iterations before it decides to inline them, and even then, that decision can be reverted if type polymorphism is detected. Go's escape analysis is equally decisive. If a struct allocated inside a function, proven at compile time to never escape to the heap, Go allocates it on the stack. This is a static guarantee. V8 must make this decision dynamically, and it will sometimes get it wrong under pressure. Dead code elimination in Go happens at link time, removing entire branches that will never execute. The result is a binary where the hot path of type checking, the inner loop that processes every symbol, every type node, every assignability check, is already the tightest machine code it can possibly be on the first nanosecond of execution. V8 needs hundreds of milliseconds of profiling to even approach that state. And here is the architectural implication that will matter when we look at monorepos. This gap widens as project size increases, because larger projects have more hot paths, and more hot paths mean more JIT warm-up debt. Startup savings and AOT optimization account for roughly 2 to 3 times of the performance gain. The remaining multiplier from a fundamentally different architectural capability. True parallelism at the type checking level. Let me walk you through exactly how this works. The Go compiler begins by constructing a directed acyclic graph of your source files based on their import relationships. Files with no unresolved inter-file dependencies are immediately eligible for parallel processing. These independent files are dispatched to a goroutine pool. Think of it as a self-managing team of lightweight threads, each costing only about 2 kilobytes of initial stack memory compared to OS threads, which start at 1 to 8 megabytes. The pool uses a work-stealing scheduler. Idle goroutines actively pull pending files from the queue rather than waiting to be assigned. This eliminates the load imbalance problem you see in naive thread pool designs, where some threads finish early and sit idle while others are overloaded. The synchronization barrier appears only at cross-file type resolution boundaries. For example, when file A's type checker needs to resolve a type that was declared in file B. At that point, the goroutine processing file A blocks on a conditional variable until file B's relevant symbols are resolved and published to the shared type cache. The critical architectural insight here is that the vast majority of type checking work, checking function bodies, validating local variable types, resolving generic instantiations within a single file, requires no synchronization at all. That work runs fully parallel. The original Node.js TSSE cannot do any of this, because JavaScript's event loop is fundamentally single-threaded. Worker thread experiments were explored and abandoned because the IPC serialization cost between threads dominated the parallelism benefit. That design constraint is now gone entirely. Parallelism, without a sound concurrency model, is just a race condition waiting to happen. So the question you must ask is, how does the Go compiler keep the shared type resolution cache consistent across dozens of simultaneously running goroutines without either corrupting data or serializing every access into a bottleneck? The answer is a read-write lock pattern that maps perfectly to the access pattern of type checking. Here is the key observation. Once a type is resolved and written to the cache, it is immutable. It will never be modified again. It can only be read. This means the lock contention profile is heavily biased toward reads, with writes occurring only once per type symbol at the moment of first resolution. Go's sync-RW mutex is designed exactly for this pattern. Multiple goroutines can hold a read lock simultaneously. So if 10 goroutines all need to look up the type of a commonly imported interface, they all read concurrently with no blocking between them. A write lock is only acquired by the single goroutine that wins the race to resolve a type first. All others that need that type will briefly contend on the read lock until the write completes, then all proceed in parallel. What makes this safe in Go is not just the mutex primitives, but Go's memory model, which provides a formal happens before guarantee. Any goroutine that successfully acquires a read lock after a write lock has been released is guaranteed to see all data written during that write lock. There is no need for volatile annotations, memory fences, or unsafe operations. Correctness is enforced by the language specification itself. This is a level of concurrency safety that would have been extraordinarily difficult to replicate in the Node.js architecture. And it is one of the concrete reasons Go was chosen over alternatives that would have required manual memory ordering. Now let's make this concrete with CPU utilization numbers, because this is the metric that will appear in your CI dashboards and will require you to reconfigure your build infrastructure. The original TSSE, despite running inside Node.js, which technically supports worker threads, was architected as a fundamentally single-threaded process. The checker point DE's type checking phase, the most CPU-intensive step, runs entirely on a single event loop. Worker thread experiments were conducted in the TypeScript team's internal benchmarks, and the conclusion was that the serialization cost of passing AST nodes between isolated V8 heaps via shared array buffer overwhelmed the parallel processing benefit for anything other than very large, highly modular projects. The result, on a modern 16-core machine, TSSE saturates exactly 1 core during type checking. CPU utilization sits at 6%. The remaining 94% of your machine's processing capacity is idle, waiting. The Go compiler's goroutine-based architecture changes this categorically. GoMaxProx, which defaults to the number of logical CPU cores available, controls how many goroutines execute simultaneously in parallel. On that same 16-core machine, the Go compiler saturates all 16 cores during the parallel type checking phase. CPU utilization during this window approaches 95 to 100%. The wall clock time for that phase drops proportionally, not perfectly linearly to Amdahl's law synchronization overhead, but close enough to deliver the 8 to 10 times range that Microsoft's benchmarks have documented. The practical implication. If you are running TypeScript checks in a CI environment and your build machines have 8 or more cores, the Go compiler will use all of them automatically. That infrastructure investment you already made, it finally pays off with TypeScript 7. But does this mean you should just throw more cores at the problem? The answer in the next section is more nuanced than you expect. Performance is not just about compute speed, it is about how well your runtime manages the millions of short-lived objects that a compiler creates and destroys. And this is where the GC architecture difference between V8 and Go becomes profoundly consequential for typed compilation workloads. Consider what the TypeScript compiler actually does to memory. It allocates an AST node for every token in your source files, a type object for every inferred or declared type, and diagnostic objects for every error candidate it considers, most of which are discarded. For a medium-sized TypeScript project with 50,000 lines of source, this can mean 5 to 10 million object allocations per compilation. V8 uses a generational garbage collector. Minor GC collections, which compact the young generation, are stop-the-world events. During TypeScript compilation, these stop-the-world pauses can occur dozens of times, each adding 10 to 50 milliseconds of latency, where all JavaScript execution halts completely. As the heap grows toward the major GC threshold, full stop-the major collection can add hundreds of milliseconds of non-deterministic pause time. The Go runtime uses a concurrent tricolor mark and sweep GC. Mark and sweep phases run concurrently with the application Go routines. Your type checking continues while GC runs in parallel. Stop-the-world pauses in Go are limited to the brief STW phases at the start and end of the GC cycle, which the Go team has optimized to sub-millisecond durations as of Go 1.42. For a compilation workload that allocates aggressively and then drops everything at the end, Go's GC simply applies less total friction. But the deeper advantage is not just GC pause reduction, it is that Go's allocator type system let you avoid heap allocation in the first place. That story in the next scene. Let's close this chapter with the memory architecture detail that ties everything together: struct layout and cache locality. Because this is the hardware level reason why the Go compiler's inner loops are categorically faster, even when comparing the same algorithmic complexity. When the Go type checker iterates over a symbol table, check whether a set of function argument types satisfies an interface, it is iterating over an array of Go structs. Go structs are value types with predictable, contiguous memory layout. If you have a slice of symbol structs, they're laid out sequentially in memory, element 0, element 1, element 2, all packed together, all accessible with sequential memory reads. The CPU's prefetcher can stream these into L1 cache ahead of demand. Memory bandwidth is used efficiently. Contrast this with V8's object representation. JavaScript objects are heap allocated through V8's hidden class system. What you iterate over when processing a type list in the current TSC is effectively an array of pointers, each pointer sending the CPU off to a random location in the heap to fetch the actual object data. This is called pointer chasing, and it is the archetypal cache miss pattern. Every dereference has a high probability of being a cache miss, which on modern hardware means a 100 to 300 cycle stall waiting for main memory. When you multiply that stall latency across millions of type checking operations per compilation, the cache miss penalty compounds into hundreds of milliseconds of wasted CPU time. Go's struct-based layout is not just a language aesthetic. It is the reason the type checker's inner loop has dramatically higher instruction per cycle throughput on real hardware. And this architecture story has a direct consequence for how you will need to think about your build pipelines and Monorepo tooling, which is exactly where we're going in the next chapter. Real-world impact on CI pipelines, Monorepo dependency graphs, and the ecosystem shifts that TypeScript 7 is about to force across the entire JavaScript toolchain. We've spent the last chapter inside the Go compiler's architecture. Now let's leave the theory behind and land on something that hits your budget. Consider a representative 200 package Monorepo, the kind you see at scale stage startups and enterprise front-end platforms alike. With TypeScript 5, the TSC phase alone runs approximately 240 seconds. That is 4 full minutes where every engineer on your team stares at a spinner before they can merge. With Type 7's Go native compiler, that same phase drops to roughly 24 seconds, 10 times faster, not as a benchmark cherry pick, but as a structural consequence of the parallelism and memory model we examined in Chapter 4. Now translate that into business language. If your team runs 50 CI builds per day at GitHub Actions per minute billing, you are burning roughly 200 minutes per day on TSC alone. After TypeScript 7, that falls to 20 minutes. At scale, that is tens of thousands of CI minutes saved per month, real money, and real developer hours reclaimed. But here is the question no one is asking yet. What does this do to your pipeline's critical path? And bottleneck becomes the new constraint. CI cost reduction is visible in your billing dashboard, but the impact on the local development loop is arguably more significant. It is just harder to put on a spreadsheet. Every TypeScript developer runs server inside their editor, whether that is VS Code, NeoVim, or WebStorm. Today, to server is a Node.js process sharing the same JavaScript runtime as the compiler itself. On a large project, go-to-definition can stall for 800 milliseconds to 2 full seconds. Autocomplete suggestions arrive late enough that you have already started typing the next token. With the Go rewrite, server becomes a native binary. Response latency for language server protocol operations drops to the 50 to 100 millisecond range, below the perceptual threshold where humans notice delay. Watch mode, which recompiles on every save, falls from multi-second cycles to sub-200 millisecond incremental checks. This is not a quality-of-life improvement. Research from Google and Microsoft's own productivity labs consistently shows that feedback loop latency under 100 milliseconds keeps developers in flow state. Above 1 second, context switching begins. TypeScript 7 does not just speed up your builds, it structurally changes the cognitive economics of TypeScript development. And that brings us to a deeper architectural question. If the compiler is now this fast, what does it mean for tools that deliberately skip type checking to achieve speed? Here is a question that every engineering architect should be able to answer in a system design review. If sbuild already builds in milliseconds, and SWC already transpiles TypeScript at near-native speed, why does TypeScript 7's Go rewrite matter? The answer requires understanding a fundamental distinction that the front-end toolchain community often blurs. sbuild, SWC, and Babel, in stripping mode, are transpilers. They parse TypeScript syntax and emit JavaScript without evaluating the type system. They are deliberately type blind. They are fast precisely because they skip the hardest part. TypeScript's compiler has always done something categorically different. It builds and traverses a full type graph across your entire codebase, resolves generics, checks assignability, and enforces structural contracts. That is where the 240 seconds goes. TypeScript 7 does not abandon that semantic richness. It delivers full type fidelity, the same correctness guarantees you have always had, at speeds that now compete with type stripping tools. This resolves what I call the historical speed-safety trade-off that has defined front-end architecture decisions for the last 5 years. Vite uses sbuild for speed and runs TSC separately in CI as a type check gate, a two-phase compromise. TypeScript 7 collapses that compromise into a single tool. But wait, does this mean the ecosystem of fast transpilers becomes obsolete? The answer is more nuanced than it appears. Speed at the compiler level means nothing if your project cannot migrate to TypeScript 7 without breaking. So let us be precise about what the ecosystem compatibility landscape actually looks like. The tsconfig format undergoes structural changes in TypeScript 7. Several legacy compiler options are deprecated or consolidated, and the new build system introduces project-level configuration keys that have no TypeScript sync equivalent. The migration tooling exists, but it requires explicit review on large code bases. The plugin API is the sharper edge. TypeScript transformer plugins, widely used in Nest.js, Angular, and decorator-heavy frameworks, are implemented as TypeScript compiler API hooks. The Go compiler does not host the same plugin surface. Microsoft's current roadmap indicates a compatibility shim, but the timeline for full transformer plugin parity is not guaranteed for the initial TypeScript 7 release. Language server protocol compatibility, on the other hand, is high priority for Microsoft. LSP is the interface VS Code depends on, so editor integration is expected to be stable from day one. The practical migration path for most teams is TypeScript 7 as the type check and language server, with existing transpile pipelines remaining in place initially, then consolidating as the plugin API matures. This is not a Flag Day migration, it is an incremental architectural shift, and that incremental pattern actually points to something larger, which we will examine in the final section. Every engineering leader eventually faces the rewrite question. And the TypeScript 7 story gives us one of the clearest case studies of the last decade for answering it rigorously. The decision to rewrite is not about technical debt in the abstract. It is about whether the current architecture has a structural performance floor that incremental optimization not breakthrough. Microsoft spent years optimizing the JavaScript-based TypeScript compiler. They introduced incremental builds, project references, isolated modules mode, and worker thread experiments. Each optimization improved things at the margin, but the fundamental constraint, a single-threaded JavaScript runtime with garbage collection pauses, incapable of true parallelism across packages, was architectural, not algorithmic. No amount of clever TypeScript code removes the GIL equivalent constraint of the V8 event loop. That is the signal. When your optimization efforts are fighting the runtime rather than the algorithm, you have hit the architectural constraint ceiling. The rewrite decision framework has 3 gates. First, is the performance floor a runtime constraint or an algorithmic one? If runtime, a rewrite in a system is justified. Second, does the rewrite preserve the semantic contract the correctness guarantees users depend on? Type 7 preserves full type semantics. A rewrite that changes behavior is a new product, not a faster version. Third, is the migration path incremental enough that the ecosystem can absorb it without a flag day break? These 3 gates, runtime constraint, semantic preservation, incremental migration, are the criteria that separate justified rewrites from rewrite-driven development as an engineering anti-pattern. In our final chapter, we will abstract these principles further into the architecture lessons that apply far beyond TypeScript. To any system where a 10x leap becomes structurally necessary, we have now traversed the full architecture of TypeScript 7's Go rewrite. And before we close, let's crystallize the entire argument into one coherent map. Every 10x performance leap in computing history shares a common pattern. It is never a single optimization, but a convergence of 3 forces: the right execution model, the right memory model, and the right concurrency model, all aligned simultaneously. The original TypeScript compiler in JavaScript inherited V8's JIT pipeline, which trades startup latency and memory overhead for eventual throughput. Go's ahead-of-time compilation eliminates that JIT warm-up cost entirely. Go's goroutine scheduler, backed by an MN threading model, allows the compiler to parse, bind, check, and emit in parallel across thousands of source files without thread creation overhead of OS-level threads. And Go's escape analysis with explicit value semantics dramatically reduces GC pressure, the single largest hidden cost in the old TSC pipeline. These are not independent wins. They are multiplicative. That is the architectural principle behind every genuine 10x leap. When your bottlenecks are structurally co-located, solving them in the same rewrite produces compounding returns. The question you must now ask about your own systems: where are your co-located bottlenecks hiding? Understanding architecture principles is only half the equation. The other half is knowing what to do Monday morning. Here are your 3 immediate action items. First, audit your current TSC phase timing inside your CI pipeline right now. Run TSC with the diagnostics, extended diagnostics flags. Look specifically at the check time and bin time metrics. If your check fix exceeds 60% of total compile time, you are an ideal candidate for TypeScript 7's parallel checker, and you will see disproportionate gains. Second, evaluate TypeScript 7 beta compatibility for your project. The Go native compiler introduces strict parse semantics in several edge cases around declaration merging and ambient module resolution. Run the beta against your codebase in a shadow CI lane before your team upgrades. Third, study the Go compiler source self, specifically the CMD compile package, as a masterclass in large-scale toolchain design. Microsoft's architects made every structural decision you see in TypeScript 7 by studying exactly this codebase. Understanding why Go was chosen over Rust, shared GC semantics, simpler FI surface, faster developer onboarding for a 300-person compiler team, is the lens that will sharpen your own platform engineering decisions for the next decade. The engineers who understand the why behind toolchain architecture choices will be the ones defining the platforms that the next generation builds on. That is where this lecture leaves you, not at the finish line, but at the starting line of a much larger conversation.